In this segment, we will consider limits of sequences. Limits of sequences is a very important technical tool in mathematics. It allows to connect many key concepts and provides underpinning for very important results. That we will use in this class too, especially in the second part of the Calculus for Life Sciences. However, today we will talk about limits of sequences as a way of thinking, because it brings certain philosophy. So sequences often arise in life sciences as time series. And if we think of a sequence as a journey from one element to another, to another, to another, then thinking about limits can be compared as thinking about a destination. What happens as we travel down the sequence all the way to the end? So today we will consider the definition, naive definition of limit, so that we understand the main mathematical concept. And we also talk about ways to compute limits, and we try to keep it practical, and we'll focus on the philosophy of it, thinking about the destination. We will start from reviewing a few techniques how to compute the sequences in a very mathematical way. But after that, in the second part of this lecture, we will bring it back to the applications of life sciences, and we will consider a special case of the sequence, the geometric sequence, the geometric series, and we will show how to use the concept of limit to work with that particular sequence. So at the end of the lecture, we will revisit the logistic difference equation, and we will show how the behavior of the logistic equation can be analyzed in terms of limits, but that's an optional portion of the class. So let's look at the motivation. Let's take a look at two sequences. I have sequence AN, and it goes as 1, 1/4, 1/9. Its general term is 1 over n squared. Its graph is on the left, over here. So what we see a certain trend that elements of the sequence approach 0. Then the other sequence that we will look at is the B sub n, and that sequence is obtained by evaluating sine of 1, sine of 2, sine of 3 radians, and eventually the general term of the sequence is just sine of evaluated on a natural number n. It turns out that that sequence will show a wave, well, because sine is a periodic function. Interestingly enough, none of these points, even though that they look like they're the same, they are actually not the same and never will be. That's a very interesting mathematical statement. There is not a single point that you can hit twice. But anyway, it will continue like that oscillating. So we notice that elements of sequence Bn do not approach any particular value as n increases. We would like to distinguish these two behaviors. On one hand, we have a sequence as the index increases, the element starts to approach value 0. On the other hand, we have a sequence as index increases, their values are continue to vary and do not approach a particular number. The concept of limit allows us to distinguish the two behaviors. Here's the definition of limit of a sequence. We say that sequence AN has the limit L, and we write it as the following statement, which I will go over that in a minute. We say that sequence has limit L if terms of the sequence A sub n stay arbitrarily close to L starting from a sufficiently large n. What does that definition mean? Well, let's take a look at the sequence. Here we have an example, 1 over n. And we notice that as n increases, values A sub n approach 0. And we can look in detail. So for example, A100 will be equal 1 over 100. And A over A1000 would be equal 1 over 1000, which is 0.01. and a over 10,000, so that would be way towards the right, would be 0.0001. So clearly these elements get smaller and smaller and smaller. So in this case, L equals 0 is the limit of the sequence. And we can expect that all of the elements of the sequence will stay close to that limit. And we can even say how close. So we can choose a particular level. Like, for example, I want to go this far. And we can see that a few elements are not close enough. So these elements are not close enough. But starting from this guy over here, these elements are they're already close to L0, L equals 0. But maybe that's not close enough for us, so we decided, how about we will look even closer and we will put a line that is parallel to the x-axis but closer. Now it's even closer to L equals 0. And guess what? Like a few of the points now staying too far, but starting from this one, so this guy is staying too far, but starting from this guy over here, all of the elements of the sequence stay below that purple line. And the claim is, it doesn't matter how close we will put the line parallel to the x-axis. Eventually, we expect that eventually elements of the sequence will go below that line and they will be squeezed between L equals 0 and that line, starting from some number. So let me write it down. No matter how close the line is to L equals 0, starting from some number n, all elements an will be located between the line and the L equals 0. And that's what definition of the sequence means. That no matter how close you put that little bound, all of the elements of the sequence will fall between the limit and that bound, starting from some number. And there will not be any element of the sequence that will jump outside of that bound. If it does, then there is no limit. We have to guarantee that all of the numbers will be within the bound. Why is this important? Because we're talking about trends. We're talking about destination. What is the destination of sequence 1 over n? That destination is 0. And if elements of the sequence will start bounce up every now and then, and if the elements of the sequence will start bounce away every now and then, 0 will no longer be the destination of the sequence. The last thing I'd like to do on this slide is to go over the notation for limits. First of all, the word limit over here indicates that we are looking for the limits of the sequence. Now, a sub n, that will make the sequence specific. It tells which sequence we work with. Now, L is the value of the limit. And n goes to infinity is standard for limits of sequences. We usually consider the cases where index goes to infinity. There are some special cases where we want to go not through every value of the index, but only through some, but that usually discussed separately. Now that we discussed the meaning of the limit of sequence and its notation, let's introduce a couple of more related notations and definitions. So we will say that sequence converges, or we say it is convergent if limit exists. If limit does not exist, we say that sequence diverges, or we say sequence is divergent. We have a different notation, alternative notation, to express that sequence AN has limit. We can say that AN approaches L as N approaches infinity. And that is just an alternative notation for the limit. That means the same as limit N goes to infinity, AN equals L. That's absolutely equivalent notations. With these definitions in mind, let us consider our first example. We have a sequence. A sub n is given by the formula 1 over n, and the question is the sequence convergent or divergent? Now, we already looked at the graph of that sequence, and we know that it's convergent, but what we're going to do right now, we will introduce a way of thinking that is very, very useful when discussing trends. So, and that way of thinking is maybe not mathematically precise, but it is very intuitive, and it's very, very useful to get meaningful results in practice. So let's think about it. I'll look at A sub n, which is 1 over n. And I know that n goes to infinity. And what it means that n gets very large and positive. Now, if we have 1 over large positive number, which would be 1 over n becomes a large positive number. So we are looking at the result of taking 1 and divided by a large positive number. Well, what would that be? Well, let's take a look. If I take 1 and divide by 0.1, I get 10. But 0.1 is not a large number. It's actually not a very small, but smallish number. Now, if I take 1 over 100, then all of a sudden I have 0.01. Now, if I take 10 to the 6th, then I get 0.000001. Now we start to see that when we divide by a large positive number, we get small. The sign, I bring the sign here in the focus because it will be essential for other things that we will do today. But the important message is that when we divide by a large number, we get a small number. And the sign is also important in some cases. Maybe not in this one. So, now as n gets larger, we'll get 1 divided by a very large positive number. So we get very small positive number. We conclude from here that as we continue to increase n all the way to infinity, A sub n would be 1 divided by n, 1 divided by a very large number will go to 0. Because the number will get smaller and smaller and smaller. So what is it we're trying to remember from this discussion? What we're trying to remember is the conceptual thinking. If you have fraction 1 divided by a large number, the result is small number. Send that large number all the way to infinity, the result will go to 0. Let us see if we can apply the same thinking again. So we would like to know, is there a limit as n goes to infinity of an where an is given by the formula 1 over n squared minus 100. Now n goes all the way to infinity. There's interesting thing here in the denominator, n squared minus 100. So we realize that for some values of n, for example n equals 10, we will have division by 0. But the important thing that when we talk about limits, we talk about trends for very large values of n. And that means that n equals 10 is not even important. we do not worry about n equals 10 because what we think about is n equals 10 to the 5, n equals 10 to the 10, and so on. We're talking about, we think about very large numbers. That's what limit is, thinking about the tendency far down the sequence. Well, if we think about those very large values, then let's take a look. So we'll have, say, 10 to the 5, then it will be squared and subtracted 100. Well, we realize that that 100 will not matter. 10 to the 5, that 100 is already minuscule compared to what comes out of here, which is 10 to the 10. Now, you go to 10 to the 10, then you can plain ignore that 100. So we will still have division of 1 by very large number. And that gives us very small number. We conclude that limit of an as n goes to infinity equals 0. And we'll put it over here. Let us take a look at another example. So here we have a sequence defined by a tricky formula. So it looks like a piecewise function, and it actually works like a piecewise function. So that sequence is defined by a tricky formula. It says if n is divisible by 5, then that element should be equal to 1. In all other cases, it's 1 over n. So let us see if we can write down a few elements of that sequence. All right, so n equals 1 is 1 divided by 1, and is not divisible by 5. N equals 2, 1 over 2. N equals 3, 1 over 3. N equals 4, okay, so it's A1, A2, A3, A4, 1 over 4. Now, A5, now the index is divisible by 5, so we get 1 here. All right, continue. 1 over 6, 1 over 7, 1 over 8, 1 over 9. Next index, 10, is divisible by 5, then we get 1. So, and then we continue. 1 over 11, 1 over 12, 1 over 13, 1 over 14, and then 1 again, because the index is again divisible by 5. And we can continue forever. If we want to take a look at the graph, it will be the following. We will see our familiar sequence, 1, 1/2, 1/3, 1/4, and then we will bounce to 1. Then we continue 1/5, 1/6, 1/7, 1/8, 1/9, and then we bounce to 1. 1/10, okay, 11, 12, 1 over 13, 14, and then we bounce to 1. So we're going to have a sequence that mostly stays around 0, but every now and then is bounce back to value 1. So here's the question. Is the sequence convergent or divergent? Now, it turns out that this sequence is divergent. For convergence, the elements an have to stay arbitrary close to the limit. And it turns out that for this sequence, there is no value for which the elements would congregate to. A potential possible limit is L equals 0, which would be right here. But guess what? Not all elements of the sequence will be staying close to it. We can put a boundary, like a little barrier, and we will see that while most of the elements of the sequence stay there, but some will jump out. And it doesn't matter how far down the line we go, there will always be elements in the sequence that will bounce away from that little region. And you can try a different value for the limit. For any value that you want to try, it will be the same picture. The elements of the sequence will not stay there. So Since we cannot find a value L such that we conclude that this sequence has no limit, or the limit doesn't exist. In this case, we say that the sequence is divergent. Next, we will consider an important practical case of divergent sequences. An important case appears when elements of the sequence become large as the index increases. That's an important practical behavior. That means the quantity becomes large positive or becomes large negative, and most of the cases we do want to know when that happens. So when we say becomes large, that means unboundedly large. It goes on the higher and higher values without any stopping, any bounds. If that is the case, when the values of the sequence become large positive and continue to grow, we say that limit of the sequence is equal to infinity. And this is what we write. Now, if the values become large negative, we will say limit of the sequence is negative infinity. So let's take a look at an example. So for example, we have a sequence an, which is given by the formula n squared, and we would like to know, is the sequence divergent or convergent? Well, let's take a look. We have n squared. We have very large number squared. When you take a very large number, n squared, doesn't matter if you start with negative or positive, you will end up with even larger positive number. We therefore conclude that limit of an in this particular example is equal to positive infinity. And please note that this is not the strict mathematical argument, but it's a conceptual thinking. You can make that conceptual thinking precise by using, for example, an epsilon language, which we often do in advanced mathematics courses. But for the sake of this course, we're not going to delve to the precise proofs, but we will go with the conceptual understanding. Take a very large number, squared, what do you get? Even larger positive number. Make that number bigger, bigger, and bigger. Your result goes all the way to infinity. Hence, we conclude that the limit is infinite. Here's another example. Here we have a sequence, a sub n, and we're again looking to check if the sequence is divergent or convergent. And in this case, the formula for the element of the sequence is like follows. You'll have -1 raised to n, and you'll multiply by 2 raised to n. Well, let's take a look at the graph of that sequence. Let's evaluate a few elements of that sequence. So the first element will be 2 raised to 1, so it's going to be -1 raised to 1 times 2 raised to 1. The second element is -1 raised to 2 times 2 raised to 2. The third element, -1 raised to 3 times 2 raised to 3, and so on. So if we simplify it a little bit, you'll have -2 plus 4 minus 8 plus 16, and so on. So -1, 2 raised to n. Now, we do know that 2 raised to 10 is 1024. 2 raised to 20 is going to be 1024 squared. So you would expect at least 10 to the 6th. So we realize that these numbers grow. In fact, they grow very fast. So we expect that we will have the absolute value to go to infinity. However, there is one additional element here that we didn't discuss yet is the sign alternation. We go from negative to positive to negative to positive. So what's going to be on the graph is that we'll start with the value and then we'll change the sign. So we'll start with a negative, then we go positive, then we go negative, then we go positive, then we go negative. Now, this is in fact an exponential function, so we expect something like that. And because of the sign alternation, we'll have a sort of reflection of that exponential function. And we expect that elements of our sequence will sort of follow that exponential function as we go, going back and forth, back and forth, back and forth. Something like that. From here to here, from here to here, then bounce here, then bounce here, then bounce here, then bounce here. So with this behavior, we notice that an will get large by magnitude, but will alternate sign. So it's a very specific behavior. It's not going to go to the positive infinity. It's not going to go to the negative infinity. It will bounce between infinities. And in this case, we will say that it's not our special case. If we would just get positive large, that would be good. We would say limit is infinity. If the answer would be negative large, we would say it's negative infinity. But if it's neither, if it's oscillating, then we say the infinite limit does not exist. We'll say infinite limit doesn't exist, and we will say here does not exist. Let us consider one additional example for infinite limits. Again, the question is if the sequence is divergent or convergent. Let's take a look at the sequence. The formula for the sequence is n minus n squared. And if you look at that, we have a competing sort of tendencies. This will get large. N squared also will get large. Well, this number is positive large, and n squared is also positive. And now we put it together, we have positive large minus positive large. And it's not immediately clear what's going to happen when you take one large number and subtract another large number from it. What is the result? It's a little bit difficult to make a conclusion. In fact, mathematically, we consider that indeterminate. Indeterminate form meaning cannot make conclusion yet. And what does that mean? That means we need to do more research. We need to rewrite the statement in a slightly different form to make the trend obvious. Okay, so what can we do in this example? There are different things that you can do, and there's more than one way to solve it. One way to see the trend is to factor out n. So factor out n, and you have now n multiplied by 1 minus n. Let us take a look at the expression n multiplied by quantity 1 minus n. And we are interested to see what trends do we have as n goes to infinity. N's going to infinity means n's becoming very large. So here we go. N is becoming positive large. What about 1 minus n? Well, if n is positive large, we will be subtracting a very large number from 1. The result is large negative number. All right, very good. Now, what we get if we take a large positive number and we multiply it by large negative. The magnitude of the product will be large, and the sign will be negative. So we get large negative number. We therefore conclude that limit of an equals negative infinity. So for the sake of this class, this type of support that you see here is sufficient for the full credit. It doesn't go into nitty-gritty detail that we usually require of the math majors. However, it shows the conceptual thinking. If you have a large positive number and you have large negative number, when you multiply them through, you get even larger negative number. So as n goes to infinity, that number becomes larger, 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 and stays negative. Therefore, we conclude the sequence goes to negative infinity. Talk a little bit about mathematical tools that help us to evaluate limits. It turns out you can do algebraic manipulations with sequences. You can add them element by element. You can subtract them element by element. You can divide them element by element. And it turns out that limits of sequences respect arithmetic operations. In particular, you can prove the following limit laws, that if limit of sequence A exists and limit of sequence B exists, then limit of the sum also exists and is equal to sum of the limits. Limit of the difference of two sequences exists and is difference of the limits. If you have multiplication by a scalar, then limit of the multiplication by a scalar exists and its limit multiplied by that same scalar. So you have all of these nice mathematical formulations. Limit of the product is product of the limits. Limit of the ratio is ratio of the limits as long as denominator is not zero. And you can raise sequence into power element by element. And if the sequence had a limit, then limit of the result will also exist, and it would be limit raised into power. So limit laws are very important because they allow you to look at a complicated expression and break it down to simpler pieces and figure out the limit by figuring out the limits for the simpler pieces and then combine it back. We also need some elementary limits. And one of the elementary limits is 1 divided by n raised to p. As long as p is positive, that limit will be equal to 0. Let us work out an example using a limit law. So we are looking to compute limit of the following sequence. In the numerator, 2n squared plus n plus 5. In the denominator, n squared minus 3. And we want to know if this sequence is divergent or convergent as n goes to infinity. Now, if we start to do just simple analysis, we have a large number in the numerator, large positive number, and we have a large positive number in the denominator, and as of right now, it's not clear to make a conclusion. And as of right now, it's impossible to make a conclusion. Large number over large number is indeterminate form. So we have large over large. As it stands, we have large over large, and that is indeterminate. Now, what we could do, we can rearrange the expression a little bit to make it determinate. So how can we rearrange the expression? We can use a technical trick, divide both numerator and denominator by a power of n. What is the power? Well, that goes with the convenience. A good rule of thumb is divide by the highest exponent of n. In some cases, it is better to divide by second highest, depending what the limit is. So in this case, it would be constructive to divide by highest exponent of n. So here we go. I divide the numerator by n squared and denominator by n squared. All right. How does that simplify? So first I distribute division by n squared to the numerator. Let me repeat, limit as n goes to infinity. And in the numerator, I'll have 2n squared divided by n squared. Then I distribute on the second term, n divided by n squared. And finally, 5 divided by n squared. In the denominator, I have n squared divided by n squared minus 3 divided by n squared. Let me simplify a little bit. So limit as n goes to infinity, I repeat. The first term simplifies to 2. The second term simplifies to 1 over n. The third term is staying the same. In the denominator, the first term simplifies to 1. The second term stays the same. Are we ready to make conclusion? Let's take a look. So 1 over n, we know that that will go to 0 as n goes to infinity. 5 over n squared, we know that 5 over n squared will go to 0 as n goes to infinity. 3 over n squared, we know n will go to 0 as well as n goes to infinity. So what is the resulting expression? It would be 2 plus 0 divided by 1 minus 0. The answer in this case is 2, and we solved the limit. Now let me highlight that in this solution, we actually got to use the limit laws. In particular, what we did, without really explaining it very much, what we actually did is the following. We made a step. We said that let's apply first of all, the law of 5. And we broke limit of the whole fraction to the limit of the numerator. Okay, it was law of 5, and the limit of the denominator. Okay, we then applied laws 1 and 2 in combination in both numerator and denominator to break this fraction into the following. Limit as n goes to infinity of just 2 plus limit as n goes to infinity of 1 over n plus, let me continue here, limit as n goes to infinity of 5 divided by n squared. And in the denominator, it is limit as n goes to infinity of 1 minus limit as n goes to infinity of 3 divided by n squared. Now, each of these limits exist. Our steps are legitimate. If these limits wouldn't exist, then we couldn't use the formula. Okay, let me move here a little bit. And to conclude the steps, we evaluate the limit. So it's going to be 2 plus 0 divided by 1 minus 0, altogether 2. Now, for the sake of training, I would encourage you to go step by step at least a couple of times so that you connect the evaluation of limits with the particular law that we use. So in particular, here we used, in this step, we used 5, but here if we use the combination of 1 and 2 over here. Doing it a few times will make you see how the mechanics work, and then you can go to their shortcuts. We did a shortcut in the first version. Let's take an additional example. I have a limit as n goes to infinity of the following fraction. In the numerator, I have n squared. In the denominator, I have square root of n cubed plus n plus 1. Now, again, if you look at a very naive way, it's large over large. If n goes to infinity, numerator is large, denominator is also large. So it's indeterminate. We need to do some work. We need to rewrite the expression right? And the trick that we want to use, and we can still use the trick of dividing by an exponent of n. Now, the thing is here that what is that power of n should be is not immediately clear. Now, you can try n squared, but it turns out to be that's not the best choice. The best choice is the following. We will take a look at the denominator. If all of these problems, you can follow very simple and yet powerful rule. When you try to solve the problem, find the portion of that problem that you don't like the most, and 99.9%, that is something that you need to attack in the very first step. So here I look at that expression and I ask myself, which part of it I don't like most? And the part that I don't like most is the square root. I don't like that square root at all. So I think I should attack the square root first. Now, what can I think about the square root? So I have n cubed plus dot, right? Inside the square root. If I think about that n cubed inside the square root, I think of an exponent of 3 over 2. Right? That would be on my radar. So here we go. We decide to do the following. We decide to try dividing not by n squared, but divide by n raised to 3/2. And it's trial and error process, always. So if it doesn't work, we'll go back and do it again and try a different idea. So let's see what we can do here. So let me distribute the n raised to 3/2. In the numerator, I have some simplification. I will have n raised to 2 minus 3/2, right? That's what you get when you combine the terms. And in the denominator, I will have the following. Let me show you. So I'll do it on the side because it's a little bit easier to do it on the side than just keep dragging the whole thing. So what do I have? I have n cubed plus n plus 1. Then I have the division, and n raised to 3/2 you can think as a square root of n cubed. Another way to think about it is a fraction. N cubed plus n plus 1 divided by square root of n cubed. Now, we have a formula, right? Square root of a divided by square root of b equals square root of a over b. So let me do that. I'll do square root, and I have a fraction here. In the numerator, I have this. In the denominator, I have this. And that simplifies to the following. Then I have, when I have a plus b plus c divided by d, that is a divided by d plus b divided by d plus c divided by d, right? So these are the arithmetic rules that I use, and I break that fraction into n cubed divided by n cubed plus n divided by n cubed plus 1 divided by n cubed. And that is what I will write here. N cubed divided by n cubed plus n divided by n cubed plus 1 divided by n cubed. So here we go. Let's simplify it a little bit. Limit as n goes to infinity. In the numerator, I'll have n raised to 1/2, because 2 minus 3/2 is 1/2. And in the denominator, I'll have 1 plus 1 over n squared plus 1 over n cubed. So now I will start thinking. Am I ready to make a conclusion? So I have this element go to 0 as n goes to infinity. That second 1 over n squared will also go to 0. And the whole denominator will go to 1 plus 0 plus 0. Now, numerator, will go to infinity. It's a positive number. I'll take a square root. It's still a positive number. As the number goes larger, square root will go larger. So it will be a very large number, positive, large positive number, and divided by 1, essentially. We conclude, therefore, the result would be large positive number, and the limit of an will be infinity. Let us consider one additional example here. We're looking at limit as n goes to infinity of sine of 1 over n. It looks complicated, but it's actually not a very difficult problem to look at. With one caveat, and I'll explain that caveat later on. So first of all, we note that limit as n goes to infinity of 1 over n is equal to 0, right? So we already discussed that. So what's going to happen, we'll have sine evaluated on a very small number. And if we look at the graph of sine, this is a graph of sine x here, as the number x gets close to 0, value of the sine also gets close to 0. As we get the number pushed in here, we will get the value of the function also be pushed to 0. So we conclude that sine evaluated on a very small number is going to be a very small number as well. And we conclude that limit of an is equal to 0. I actually have to make a very important disclaimer. In this problem and in the problems above, we use the concepts that we have not discussed yet. These concepts are limit of functions and continuity. It is possible to bring the mathematical rigor and discuss this topic in the sequence they all rely on each other, but it'll probably be not super important for this course. In this course, we will necessarily go back and forth and we'll use the concepts before we actually introduce the concepts, but it will reflect the applied nature of the course. In real life, we can always do a graph of the function, and we see there that the function is continuous before we even define what continuous is. So, nevertheless, I had to make that disclaimer. We did use the concept of limit of functions and continuity that we haven't introduced yet. And if it raises any questions with you, I'd be very happy to answer those questions in class or